Everybody, I'm going to talk about mass spectrometry in this video. So keep in mind, this is going to be a very broad overview of using mass spectrometry in terms of product analysis, like unknown determination type of things. So mass spectrometry is a very, very large subject. It's got a lot of little intricacies in it. So we're just going to be doing the very, very surface level look at this. So don't use this video as that if that's what you're needing. So what we're going to be mainly getting from mass spectrometry data is it's going to help tell us the molecular weight of a compound. Okay, so it's telling us data on the mass of the compound. It relies on ionizing the compound, and then basically what it does is it ionizes that compound, and then those ions go and hit a detector that tells the detector the mass to charge ratio. Okay, so typically for small molecules, the Z, which is your charge, mass over charge, it's often +1. So most of the time your mass is going to equal your molecular weight of whatever piece is actually hitting the detector. The thing you want to keep in mind is that there's a lot of opportunities for fragmentation to happen because the ionization process is not the most gentle. So we're going to see what that looks like. For large molecules though, like proteins, for instance, your charge might be larger than +1. So that might, in that case, your M is going to mean slightly different things because you're kind of doing divisions and stuff. So this is an example of a mass spectrum, okay? Notice that we kind of have like clumps of peaks in here at different M over Z places. So that's part of the fragmentation that we're seeing here. So a lot of this stuff is all fragments that once your compound has been ionized, it's going to start to crumble into pieces that are going to be a little bit more stable and be a little bit more persistent in order to reach the detector in the instrument. So basically, when we're looking at this, the most important thing that we want to be focusing on is this right-hand peak over here, which is the molecular ion peak. Okay, the molecular ion peak is going to be the largest piece that hits that detector. And typically that is going to mean that it's kind of the one that was it wasn't fragmented, it was just ionized, and so it's pretty much the same molecular weight as what you're looking at. But notice how I said the far right, right? So the largest piece. But I didn't really go farthest to the right because I have this tiny little bitty guy over here, which is even further to the right by about 1 mass over charge unit bigger. Okay, so this one is your M+1 peak. Okay, and that's actually an example of an isotope effect showing up. Okay, so if we look at carbon typically shows up as carbon-12, but we also have an amount of carbon-13 in natural abundance just kind of on Earth. So carbon-12 makes up about 99% of carbon atoms, and carbon-13 makes up about 1% of carbon atoms. So typically when you see this, you're going to see kind of a larger one and then a little bitty one right next to it, one away, that's accounting for this carbon-13 just showing up in a certain number of places, okay? So it's just having carbon-13s hit that detector kind of 1% of the time. So that is going to be from your carbon-13. So typically you're going to look at the 2 furthest right ones, then use the larger one of those 2, and that's going to be the one from your carbon-12. Oops, not 13. Okay, so that's kind of what we're looking at. We're not going to worry too much about fragmentation patterns here. There is a lot of work that goes into that. So it's definitely a large aspect of science that is heavily researched. We're not going to worry a ton about that. We're going to mainly focus on the molecular ion peak. Okay, so one other little trick is that if your molecular ion peak is odd, then that is going to signal to you that you've got an odd number of nitrogen atoms present. Okay, and that's just to do with the bonding that nitrogen does and the molecular weight that it is. It's going to help us get to an odd number where everything else will be even numbers. So unless you have two nitrogens, and then it gets really tricky. Okay, so then there's also a couple special isotopes that we need to talk about. So bromine and chlorine both show up as special isotopes in more obvious ways than the carbon-12 versus 13. So if we're looking at chlorine first, so I've got chlorine 35 and chlorine 37. 35 shows up in about 75% natural abundance to 25% for chlorine 37. So if we're looking at kind of what our molecular ion peak would look like, you would have one that was about 3/4, another one about 1/4. Okay, so we're looking at something like this, and you're gonna have, this one is gonna be your molecular ion peak. And then this one would be your M+2 for the difference of 2 in these two isotopes. Okay. Our bromine is going to be fairly similar. So if we're looking at bromine, they actually have a pretty even mixture of bromine 79 to bromine 81. They show up about 50-50. So we're going to have approximately even heights of doubled peaks. Okay, so we're going to look. This one would be our molecular ion. And then the next one would be our M+2. Okay, like that. So these are really nice patterns to be looking for to kind of signal to you that you've got a chlorine or bromine present. To make sure that you're taking that into account when you are putting together your formula at the end of the day. So that's kind of what we're trying to get to through all of this is we have the molecular weight number, but we really, really want the formula, the molecular formula, so that we know how many carbons, how many hydrogens, how many other things, so that we can start trying to draw something that would be reasonable with the data that we're given. So that's what we're going to do. This is what we're going to focus on next. So if we've got the molecular ion peak and we're proposing formulas for it, okay, the next thing you want to do is looking for any evidence of heteroatoms. So heteroatoms including oxygen, nitrogen, chlorine, bromine, etc. These are going to be kind of the more common ones that we're going to run into. And that's going to be in any of the data that you've got. So IR, NMR, mass spec, any of those that tell you that one of these might be present, look for that evidence first, okay? And then just go ahead and subtract that mass from your molecular ion. So for oxygen, it would be 16, for nitrogen, it would be 14, chlorine would be 35, bromine would be 81. Okay, we can just fill those in really quick. 16, 14, 35, 79, right? Yes. Okay, so in all cases, we're basically taking the smaller isotope. Okay, so carbon, well, you take the 12, chlorine, you take the 35, bromine, you take the 79. And as long as you're taking kind of like that second peak from the right, then that's going to be what you're looking for. So subtract that mass from your molecular ion peak. Then you're going to take the remainder of that number and divide that by 12. 12 because we're looking at how many possible carbons might we have in this molecule. Okay, so carbon 12. If the remainder is a reasonable number of hydrogens, and I know that this is super vague and annoying, but this is something that as you get more practice here, it will make a lot more sense. But if it's a reasonable number of hydrogens where you're saying like, you know, a typical hydrocarbon would be something like CN and then H 2N plus 2, okay? Something similar to that, but it can have slight variations off of that based on rings and pi bonds and things like that. Then great. That's probably the remainder is probably just all of our hydrogens. But if that number is not reasonable, so say you've got something like 7 carbons and like 2 hydrogens, that's not really reasonable. At that point, you're going to substitute some carbons for hydrogens, okay, just to kind of trade them off. And then it's a little bit of a guess and check, okay? This is the way that I do it. It works for me pretty well. But again, this is like anything that if you find something that works for you, you stick with that. Okay, so let's take a look at this one just as an example here. So the first thing that hopefully is kind of shining out at you here is what we have going on over here on the right. I'm not looking at any of this. I'm just kind of ignoring that part. But looking over here, I can see pretty clearly that I've got 2 pretty evenly sized peaks. And then I've got 2 little mini ones right next to that adjoining it, okay? So if we're looking at this, this is kind of a fun little compilation of a bunch of isotopes happening, where this is going to be our molecular ion peak. Okay, then we have the teeny tiny little evidence of the carbon-13, the M+1. Okay, and then we've got another one. Okay, so the fact that they're kind of evenly sized in 2 of them, we're looking at a bromine, okay? Because this is going to be our M+2. Okay, so in this case, the axis here is definitely not well labeled, so I will tell you what the number is supposed to be. The number is supposed to be 156. Okay, so we're going to use a molecular ion peak of 156, which is this one. Okay, so 156, we have a bromine, so we're just going to go ahead and subtract the bromine from that. So we're going to take off the 79. So 156 minus 79. And that's going to equal 77. Okay, so from 77, I'm going to see how many carbons I can put into that and divide that by 12. And I've got 6 and change. Okay, so I can put 12 into 77 6 times. Okay, and I've got some amount remaining, and I realize that I lost the N in remaining over here. Okay, with some remainder. So the remainder is going to be 5. Okay, 5 remaining. Oh, I should just put it up here. Okay, so at this point, if I'm just kind of sticking with this right here, I'd be looking at something that was C6, H5, Br. Okay, and then we have to think like, does that make sense? Is it reasonable? Should I be having more or less of something? And does it add up to the right number? So I would start just by checking to see if it does add up. So we're going to have 6 times 12 plus 5 times 1 plus 79. Just to make sure that we did all of our math right. Okay, so we check out there, we are at the molecular ion peak. And then thinking about whether or not we can actually draw something like this. Don't be too fooled when they're kind of fairly even numbers, because that could indicate something like a benzene, right? Benzene has an even number of carbons and hydrogens, 6 of both. And if I was to take away one of those hydrogens and put a bromine on there, that would be a pretty reasonable structure there, okay? And this is, in fact, the mass spectrum for bromobenzene. Okay, let's look at another example. So I've got a molecular ion peak of 125. If I've got 125, it's an odd number. So I'm immediately going to take into account that I've got a nitrogen there. So we're going to go ahead and subtract 14 from this for our nitrogen. And we're going to just start off assuming that there's only one nitrogen and not going crazy past that. So 125 minus 14 is going to be 111. Okay, so once I'm at 111, let's go ahead and see how many carbons I can put in that. And divide by 12. And that is going to equal 9 with 3 remaining. Goodness, I keep on putting. Okay, so if I'm looking at this right now, I've got C9H3N. That seems a little wild. I cannot imagine myself being able to draw a reasonable structure here, only having 3 hydrogens to work with. That is rough. So we are going to say, maybe we should put a little sad face on that. Doesn't seem like enough hydrogens. So then we can go ahead and say, okay, what if we had only 8 carbons and take one of those away and then have 15 hydrogens? Okay, so then we would have C8H15N and see if that makes it a little bit more reasonable to draw something out. So let's see if we can draw this. So 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8, 12. Okay, so I'm just going to count this out because I need to count up my hydrogens for myself here. So 2, 4, 6, 8, 10, 14, 17, 19. So we need to take away some hydrogens here. So let's add a few double bonds. So now I've got 2, 4, 5, 6, 8, 10, 12, 15. Okay, this is looking like a pretty reasonable structure. I'm not too worried about that. Okay, so that's looking like a pretty decent formula for this mass. Okay, and again, we'll follow up with our final little check. So 12 times 8 plus 14 plus 15 is 125. Okay, just to double check that we did our math correct. All right, so then we've got another one, 112, and we're looking at this and saying, let's say we have some other data in addition to our mass spectrum, and from our IR, we can see that we've got a carbonyl or something. So I'm going to start off by taking away an oxygen. So we're going to take away 16 to start, which is going to be 96. And then take how many carbons we can have out of that. And that is an even 8. That's probably not very reasonable with no hydrogens. Probably not. So let's go ahead and reduce that down to 7. Okay, if we go to 7 carbons, then we would have 12 hydrogens. Okay, so then if we've got something like C7H12O, and see if we can draw something fairly reasonable from this guy. So I've got 1, 2, 3, 4, 5, 6, 7. Put a ketone in there just for fun. So 3, 6, 8, 10. Need to put one more pi bond in there. Okay, and then we've got 3, 6, 7, 8, 10, 12. Perfect. Okay, so we've got something like that. It looks like a pretty reasonable structure. That's not a bad one to go on. And again, we'll do our little double check here. So 12 times 7 plus 12 plus 16 is 112. Okay, so that's kind of how we're going to be using mass data. It's gonna this again, this is the very kind of overview here. So as always, let me know if you have any questions, and I will see you all later.